So let's consider a pendulum and something that is moving in simple harmonic motion and try to visualize what the motion looks like. Well, we all understand the pendulum is moving back and forth, and when it goes a certain distance from the equilibrium position that way, a force pulls it back to the other side and back and forth. And we can understand, we can kind of picture this in our minds, but it would be very helpful if we could draw this relationship on a piece of paper instead of having a pendulum in our hand. So I want you to imagine now that we're going to draw the motion of this pendulum. Think about it as taking a marker and having it touch the bottom of the pendulum. And we'll have the pendulum just barely contact the surface that it's moving across. So as the pendulum moves back and forth, it makes a mark. Well, that mark would look something like this, wouldn't it? That as the pendulum swings back and forth, the marker is going to make a straight line. Depending on the period of the pendulum, if the pendulum is swinging slower, it's going to have a bigger amplitude and make a bigger line. If the pendulum has a small period, swinging back and forth over a shorter period of time, it's going to make a smaller line. But this really doesn't tell us anything. The world is not necessarily still. Time moves. So a better representation of this would be something like this, where we get a piece of paper that is advancing as the pendulum is drawing. Let's take a look at what we get. Now for that, it's really hard to actually put a marker at the bottom of a pendulum. So instead, I'm going to move my hand back and forth like this to simulate the motion of a pendulum. But we're going to advance the paper at the same time. And this is kind of representative of time moving forward as something else is happening. So here we go. I'm just going to move my white. You'll notice my hand is going to stay right here in the screen. I'm not going to move it this way or this way. It's the pendulum moving back and forth. So I'll start in the middle, my equilibrium position. And as I pull the paper, my pendulum swings back and forth. And this is the shape that I get. I get a wave form, because it takes the shape or the form of a wave. Graphing the motion of something in periodic, simple harmonic motion makes a waveform. For those of you that are familiar enough with the math, you recognize this as being a sine wave. This is a graphical representation of the motion of something in simple harmonic motion. Right here is my equilibrium point. That was the middle where we started. It moves up here, then came back to the equilibrium position, and then goes to this displacement. It's going back and forth. Now, not all pendulum motion is the same. Sometimes pendulums move back and forth quicker. They have a shorter period. And that's what I'll show us now. I'm going to move my hand back and forth more quickly. Starting the equilibrium position. Okay, we had a quicker back and forth movement. We had a shorter period, but look at the amount of waves. The waves are more frequent here than they were before. But the waves here were bigger than they were here. So what we have here is a higher frequency because we see the waves are more frequent. Well, how do we get the higher frequency? I was making a shorter period. And we know this to be true because period is 1 over the frequency. So as one increases, the other has to decrease. So now let's do the opposite. Let's move my hand back and forth really slow. So something like a really long pendulum that has a really long period. So I'm going to pull the paper the same, but I'm going to move my hand back and forth very slowly. You can see what happens. I don't have waves as frequently occurring. My frequency went down as my time to move across the page went up. So once again, this reinforces the notion that frequency and period are inversely related. So let's talk about waves and how this relates to simple harmonic motion. Now, when we talk about waves, we're not talking like, what we think about with our traditional waves, although there is a connection. Think about when you wave at someone. You move back and forth over the same path at a certain rate over a certain period of time. Well, that's that simple harmonic motion, and that's how it relates to waves. Now, we're going to break this down a little bit simpler. I want you to think about atoms out there in the real world. What we don't realize, because we don't see it, is that most stuff is actually wiggling out there in nature. We've got these little atoms that make up everything that are wiggling back and forth. A wiggle is a back and forth motion, not a motion from point A to point B, but a wiggle back and forth. These vibrations from something wiggling back and forth, a wiggle in space-time, is what a wave is. A good, simple definition of a wave is that it's a wiggle in what we call space-time. So I've got an atom that is wiggling, and it is in a certain space, and there's a time frame associated with its wiggling. Well, that's what a wave is. A wave is a vibration or a wiggle in space-time. Now, I want you to think about, what does it take in order to wiggle? In order to do anything, what you need is energy. It takes energy to do anything. And even an atom just wiggling back and forth has some energy associated with it. So therefore, these waves, these wiggles in space-time, have to be associated with energy. So let's tie this to our study of pendulums. And we can see how a pendulum is wiggling back and forth in space for a certain amount of time. Well, that's what a wave is. A wave is a wiggle in space-time, and that takes energy. And we know that with a pendulum, there is a potential energy that then transfers to kinetic energy and then transforms to potential and back and forth again. So a better physics definition of what waves are is this. Waves are transfers of energy through space-time. So there's our better definition. And don't get bogged down in what space-time means. This is something we'll cover a little bit more extensively later. But for now, just realize that anything that's moving in simple harmonic motion, anything that is wiggling, does it in a certain space, and it does it for a certain amount of time. So in our last presentation, we talked about how we get the shape of these waves, that when a pendulum moves back and forth, it traces out a certain height above the equilibrium position and then below. That's in this space. But remember, time is moving, so as time marches on, it's tracing a shape like this. We got this typical waveform that looks something like that. And this is very similar to my pendulum, that when a certain height displaced from equilibrium, and then when a certain distance displaced below equilibrium, because it's a pendulum swinging back and forth over a set distance. And we get this shape. So this is our wave shape, and it kind of looks like a wave like we think of with waves in the ocean, which is very similar. Now, these waves have certain points where we're very interested in the wave. If you thought about our pendulum going back and forth, when we were looking at pendulums, we were very interested in that point at which it got furthest out here, the point it was back at its equilibrium position, and the furthest point that it got out here. Those were very special points, and we see that in our waveform here. Here is our point where we are furthest away from equilibrium on this side of equilibrium. And we came back to the equilibrium position, and then we went to the other side of equilibrium. So those points right there are important to us because they tell us something about the motion of this pendulum or anything that is in simple harmonic motion. How long does it take to get from here to here, back up to there? Has a name. We know that is the period. On a graphical representation of our wave, the period is how long did it take from the pendulum to go from here to the lowest point back to the next highest point, because it's where it started, goes to the opposite side, and back up. Now, we don't have a pendulum moving here. Remember, this could also be a spring. This could be anything that is exhibiting simple harmonic motion. So these points here are very important. On our wave shape, the high points are called crests, and the low points are called troughs. The distance from one crest to another is important because the time it takes it to go from one crest to another is that period. So this distance from one crest to another is important, and that is called the wavelength. And you can kind of see that's how long my wave is. It's from this wave to the next wave. Now, with wavelength, we need to define this a little bit more precisely than just one crest to the other. The wavelength is actually the distance from any two successive identical sections or points on the wave. So right here to right here is also a wavelength. Not right here to right here, that's only half the wave. But remember, to complete one cycle to get back to where you were starting from, that's a wavelength. We could say right here, go down, come up, back to that same point. That distance is also a wavelength. But it's the same no matter where you measure it from. So the wavelength is the distance from one point on the wave to the next identical point on the waveform. So let's consider a different waveform this time. Imagine my pendulum, and instead of just moving this far, instead of just moving that far from equilibrium, imagine that my pendulum moves this far. Well, my crest on my wave is going to be higher, and I'm going to get a waveform something like this. Okay. Now, say to yourself here, what does it take to make my pendulum be more over here or farther from the equilibrium position? Think about if you were physically moving the pendulum. To displace it further takes more energy. So this height of the wave corresponds to the energy associated with the wave. And you think about waves on the ocean. You're standing in the ocean and you get hit by a wave this big versus you get hit by a wave this big. You'll feel a lot more energy associated with this wave. And that makes sense because it's like my pendulum is being displaced further. And that takes more energy. You end up having more potential energy the further away you displace the pendulum. So this height of the wave is associated with the energy. The higher this height, the greater the energy of the wave. This height has a name. It is called the amplitude. The amplitude is the height of the wave, and it tells you the energy associated with the wave. Now, one thing you'll notice about these two waves, this wave's got more energy, but it has the same wavelength. So two waves can have the same wavelength. In this case, they would have the same period, but one has more energy than the other. What we have yet to examine is the frequency, because we know the frequency is directly tied to the period. If these two waves are coming along at the same rate, and we can see they have the same form, these two waves have the same period, and hence they have the same frequency. So let's examine these two waves. You'll notice they have about the same height. They have about the same amplitude, or they are associated with the same amount of energy. But the wave shape is very different. This one here has a very long wavelength. This one here has a very short wavelength. Let's talk about the frequency. If you were watching these waves come by and you were timing how often or how frequently these waves come by, you would get a bigger number than if you were looking at these waves. So the frequency at which the waves come by seems to be tied to this wavelength. As the wavelength gets bigger, the frequency gets smaller. And if you were watching these waves and you were watching them come by physically, like waves in the ocean, they would come by at a certain speed or a certain velocity. And the speed at which a wave comes by is directly tied to its frequency or its wavelength. Because you can see, man, these waves are coming by quick. They're very frequent. These waves are coming by very slow. And there is a mathematical relationship between wavelength, frequency, and velocity. But there's one other factor we need to look at. Getting back to our pendulum and how it moves back and forth, the time at which it takes to move back and forth and generate that wave shape. If I were to run this pendulum with the end of the pendulum moving through the sand, would its motion be the same? The answer is, of course, no. The sand would retard the motion a lot more than just swinging it through the air. So my characteristics of motion of my pendulum are going to be very different depending on what it is swinging through. If it was swinging through water versus swinging through air or swinging through sand, it's going to change the time at which it takes to complete one oscillation, which is then going to affect the speed of the waves that are generated. So wave velocity or wave speed depends primarily on only one factor, and that is what we call the medium. The medium is the material through which the wave is traveling or through which its energy is being transferred. Wave velocity is a constant. Waves move at a certain speed depending upon what medium they are traveling through. And for now, we'll use sound waves as an example. We will study sound more directly in the next unit after this. But sound travels at 340 meters per second in air. That's it. The wave speed is constant depending upon what medium it is traveling through. Now, sound travels a lot faster through other materials. It also travels slower in some other materials. But given a certain medium, the speed of a wave is going to be constant because it depends on the medium only. Now, there's a mathematical relationship now that is going to relate the velocity with what the wave looks like. This is the Greek letter lambda. That's F. This is wave velocity, or speed, if you will. This letter represents the wavelength of the wave, and this is the frequency of the wave in whatever medium it is traveling in. So let's examine this. We know that the velocity is constant for whatever medium it is traveling in, and that the velocity is the product of the wavelength and the frequency. So let's say this is a typical just run-of-the-mill wave, and it has a certain wavelength, distance from here to here, and it has a certain number of waves that are coming by over a given period of time. Now let's change one of these variables. Let me say I want to draw a wave with a more frequent or higher frequency. So the frequency went up. Now, the speed of the wave has to remain the same because the velocity in the medium is constant. So if this went up, in order for this to be the same, this must go down. So here was my wave, and I made the frequency go up. I made the waves more frequent, but you'll notice the wavelength has now gotten smaller. So as one goes up, the other must go down because together their product has to remain the same value. But let's do it this way this time. Let's make the wavelength bigger or longer. And you can see here, my wavelength has now gotten bigger. If this one has gotten bigger, that means this one must have gone down. And you can see that the waves are coming along less frequent. There's a lower frequency. As one goes up, the other must go down. And keep in mind, this is for a particular medium. So if we're talking about sound, and sound travels from air and then into water, well, then it has a new velocity, and these things are going to change. But the relationship always holds true. The velocity of a wave in a given medium is the product of its wavelength times its frequency. Let's talk about the units of wave velocity. Well, velocity is a wavelength times a frequency. So my wavelength is a length. It's going to be measured in some unit of length, like meters. And we know that frequency is measured in hertz. So I get meter hertz. But if you remember, a hertz is a 1 over a second. So I end up with meters times 1 over a second. I wind up with meters per second, which that makes total sense for a unit of wave velocity. Now, if it were really small waves, I might measure in millimeters or nanometers, but it's still some unit of length per second because frequency is hertz, which is 1 over seconds. There are two main categories of the types of waves. They're called transverse waves and longitudinal or compressional waves. A transverse wave is kind of what we think of. It looks like this. It's like waves on the ocean. What's true about a transverse wave is that the particles of the medium are moving at right angles or perpendicular to the motion of the wave. So with a transverse wave, this is like waves on the ocean. And if you had something sitting on the ocean, like a buoy, something that's floating, as the wave comes by, the water moves up and then the water moves down. You'll see something like a boat on the ocean. It doesn't ride with the crest of the wave. It stays in position and it's going to bob up and down. That's 90 degrees to the direction that the wave is moving. That's a good example of a transverse wave. However, you can also have what's called a compressional wave. Our transverse waves, going back to simple harmonic motion, is more representative of our pendulum swinging back and forth. I have my graph going this way, so my wave shape is coming this direction, but my pendulum is moving at right angles to my paper that was being drawn on. Our spring and mass systems, however, didn't move like this. They moved this way. Think about our spring and mass systems. We had something, we stretched the spring and it moved this way, and then it came back and forth, and it was moving back and forth like this, as opposed to this way. So the wave shape is moving this way, and the medium, the spring, is actually moving the same direction. It gets its name from a longitudinal or a compressional wave. I like compressional wave a little bit better because we can see it. Here's my spring, my slinky, and I've got it stretched out, but I'm going to squeeze together. I'm going to compress part of my slinky over here. The slinky is my medium. I've taken some energy and squeezed it together. If I let go of it, you can see the energy is being transmitted this direction, and it makes the spring, the slinky in this case, vibrate this direction. It doesn't vibrate this way. It vibrates in the same direction as the energy was transferred. So that's what makes a compressional wave different than a transverse wave. So my longitudinal compressional wave, the particles of the medium move in the same direction as the wave. Think about my spring being squeezed and stretched in the same direction as the energy is being transferred. So now you've got your basic background knowledge of waves. You need to show me your notes to prove that you have done something today, and that will earn you your daily grade, your done stamp. And after that point, I'm going to assign a quick check for understanding, a notes check, if you will, that proves to me that you have listened, paid attention, and you learned something from this presentation.